Hello everyone, I'm Jaehoon Choi. Today I'll present our work, LTM Lightweight Texture Mesh Extraction and Refinement of Large Unbounded Scenes for Efficient Storage and Real-Time Rendering. This was the research project I worked on during my internship at Meta. Current neural rendering can produce photorealistic rendering quality. We focus on mesh-based neural rendering because mesh is still widely used for most graphics applications. Given multi-view images and corresponding poses, our task is to generate a lightweight mesh, texture, and view dependency MLP for neural rendering. Mesh-based neural rendering method usually focus on either making the renderings look good or obtaining the accurate mesh geometry, but we are aiming for a three-way balance: precise geometry, efficient disk storage, and high rendering quality. All three aspects are crucial for AR and VR applications. This is the overview of our pipeline. It consists of three steps. First, we initialize geometric and appearance neural field. In mesh processing, we extract the mesh and apply mesh simplification for creating lightweight mesh. Then we optimize the appearance field jointly with vertex deformation while defining the mesh topology. We first initialize neural fields for both appearance and geometry. To handle geometry, we use the baked SDF method to train the neural scion distance field. And for appearance, we employ MIMNEP 360 techniques to train the neural appearance model. In large-scale scene, meshing neural SDF faces two issues: insufficient grid resolution for nearby objects and poorly learned geometry of distant objects. During Marching Cube, we set a final grid resolutions for central region and a coarser resolution for background. Also, we applied geometric-aware mesh decimations techniques to remove redundant triangles for flat and smooth regions. Lastly, we jointly optimize appearance field and mesh vertex deformation. Here we use differentiable rendering to fine-tune appearance field for rasterization-based rendering and refine mesh surface for detailed geometry. Here's the visual comparison of the mesh before and after decimation. Our method preserved the detailed geometry in the central areas like base and table, while making the background regions coarser but less noisy. When comparing to nerfed mesh, our method shows sharp details of complex shapes like base and stump, as well as it can represent smooth surfaces without any bumpiness or noisy surface. Our method shows higher quality rendering than nerfed mesh and also requires less disk storage. This is the visual comparison of rendering quality between baked SDF and our method. Even though baked SDF offers better rendering quality, our method can achieve comparable result with just consuming 11 times less disk storage. Our method has limitations. Specifically, the gradient-based mesh optimization can cause self-intersections and flip triangles, which could restrict the applications like physics simulation. Here we have a video demonstrating our method rendering on a VR device. We are using the Quest device to show real-time interactive rendering for VR applications. Thank you for watching the video. We will present our work on Wednesday poster session 2 and number 21.